So what you see here are, let's say, canonical agreed upon examples from each of the class. So there is something that we can call the class 1. So here have in mind the picture at the top left, which is like a the dynamics quickly, all of this is informal, have that in mind. We're just building some intuition. Dynamics quickly converge to a fixed point, typically a homogeneous one, so either all zeros or all ones. So fixed point is just the limit cycle of length 1. Class 2, what we could have in mind is a picture at the top right, which here is the rule 108, which now you can convert back to its rule table. So here the dynamics quickly converge to periodic behavior. Then the class 3 has an iconic example of rule 30, which is in some vague sense connected to chaotic behavior. So specifically, Wolfram even got a patent for the rule 30 as a pseudo-random number generator. But it has been shown that it can be attacked in some ways, but there's still a lot of open problems about the dynamics of rule 30. So class 3 is no apparent structures form in the space-time diagrams okay, let's just. And lastly, class 4 also has one canonical example among elementary cellular automata, which is rule 110 that you see in the bottom right corner. Let me just double check. I am here. Okay. So how do we describe this? So there's some emergence of local structures, which we can also call solitons or gliders. That interact with each other in complicated ways. So we can, to further build up the intuition, connect to these classes some more. Yes? Okay, okay. I think I don't remember, so you can ask now.
I just wanted to know, do we prefer to study the even rules because the 0, 0, 0 gives 0, or is that?
This is a coincidence. Yeah.
So, like, we don't have more chaos because of like, if 0, 0, 0 gives 1, does it make the cellular automata worse? Or
Not necessarily. So I could have instead shown you an example of odd cellular automata, but it so happens that the two canonical examples for the two most important classes, which are 3 and 4, have odd numbers, but there are even numbered rules here also. Have even numbers, but there are odd numbered rules here. So yeah, interesting observation. I did not realize this. Yeah. So to further develop this intuition, we can connect each of the class to some more tractable properties. So typically, it makes sense to group together the classes 1 and 2. And here we have short transients to short attractors. Very low compressibility. Or, okay, compressibility to a low number, so let's say high compressibility. That's probably clearer, thank you. High compressibility of space-time diagrams. And we can say, let's say, correlation of cells in different space and time too high for information to propagate. And maybe one last is that if you make a small perturbation to a particular initial configuration, it's going to very quickly die out and you will get the same result in some sense. So low sensitivity to local perturbations. On the other hand, class 3 is, as I said, somehow connected to chaos, but there is no one consensus on how to define chaos in discrete dynamical systems. Yet some properties that are quite typical is, let's say, long transients, too long, or too long cycles. Low compressibility in the sense that if you pick your favorite compression algorithm to compress the diagram, the value is going to be high. Correlation is 0 in some sense. Correlation is so low that information cannot propagate. And local perturbations quickly spread. And now we get to this class 4, which is in some sense a big mystery. Not only is it unclear what are the formal properties, in some sense we could say the transients are somehow not too short or not too long. The compressibility is not too high and not too low, because there are some structures, but they interact in complicated ways. The correlation is not too high for the information to die out, but not too low for the cells to be uncorrelated. And the sensitivity is somewhere in between. So if you perturb smartly, sometimes it might show and sometimes it might not. So this class is a bit of a mystery. And to make the mystery even bigger, let's say Stephen Wolfram made this hypothesis that class 4 are those CAs capable of universal computation so hopefully if we have time towards the end of the course, we can show some metrics that kind of find interesting class 4 behavior where you see these localized structures. In 2D, it's a bit more easy to spot them than in this one-dimensional case. But essentially, you have this triangular static background, and through it, you have propagation of these local structures that now interacted and transformed into a different one. So it's a bit. But as we will delve into what does it mean for cellular automata to compute, we will discuss that indeed some dynamical properties which are too rigid or too chaotic lead to the inability to compute. But we are far from actually proving this hypothesis. And one more reason why, well, so this classification is informal, but what becomes problematic if we want to look at cellular automata beyond the elementary class is that one thing the classification of Wolfram does not address is what type of initial configurations should we use when we look at the space-time diagrams. So the typical choice is either to randomly generate them uniformly or to just start with a single alive cell that is surrounded by zeros. But that really only looks at very specific subspaces of the initial configurations. And maybe for elementary cellular automata, the rules are so compact that they really behave in their typical way from most initial configurations, but this is certainly not the case in larger CA spaces. As you will have a chance at the exercises to construct a cellular automaton with more states, which behaves in a very specific region as rule 30 and in a very specific other region as rule 110, it then becomes kind of unclear how should one classify this. So let's just use this as a heuristic. But just to build some intuition for what could be considered a class 4 rule, I'll show you 3, let's say, very famous examples. So, okay. Examples. So, astonishingly, even in the very compact class of elementary CAs, rule 110 has been hypothesized for a long time and eventually proven in a way that is very elaborate that it is Turing complete, which then gives some kind of undeniable proof that it is complex in some sense. Then you probably all know of Game of Life, which was also, it was quickly realized that a lot of the dynamical properties are hard to predict. For instance, can there exist configurations which will eventually not die out against a static background was one of the first open problems posed, I think, by John Conway and quickly answered by the construction of a glider gun that just keeps on firing these gliders. But then it was also shown that it is Turing complete and even stronger notions of computational universality that we will talk about. So for instance, Game of Life is capable of some universal self-replication. And the last class are the so-called larger-than-life rules. So in some sense, this is a generalization of Game of Life. So it's parameterized by a 5-tuple. R beta 1, beta 2, gamma 1, gamma 2. And it is a class of 2D CAs with states 0 and 1, and where R is the radius. So this family is indeed infinite, because we can have growing radii. Bless you. And then suppose that K will denote the number of cell's neighbors that are alive, that means in the state 1. So there's essentially 2 rules. If cell is alive, it stays alive if it has enough alive neighbors but not too many. So this is, let's say, the survival interval. And if cell is dead, it becomes alive if the number of alive neighbors is in this, let's say, birth interval. So yeah, this space has been explored also quite thoroughly, and there have been many interesting gliders. You see the faces, 4 faces of one such glider in one such rule. And it's quite nice, as it shows that the particular interesting behavior of game of life is not specific to one single cellular automaton, but can be found in many automata from this, let's say, more general family. Yeah. So I think that concludes this intuitive intermezzo. And now we can go back to a bit more of a formal approach. I will let you have a look at it for a bit longer, but yeah. So this is, let's say, the last mini chapter of this introduction. So suppose you would like to gauge some intuition for what happens beyond the elementary cellular automata, and you still stick to dimension 1 and just 2 states, but now you increase the neighborhood by 1. Then the number of CAs in this family is 2 to the 2 to the 5. So even this most simplest change already gives a class that is somehow infeasible to study exhaustively, which motivates ways to reduce the size of these spaces so we can still have some exhaustive overview of some subset of them. And there's essentially 2 ways. So one method is to restrict the form of the local rule. So in some sense, we have already looked at local rules being invariant under certain group actions. So 2 famous examples of this. So there was the rotational symmetry ones. So the first one is, let's say, totalistic cellular automata. So A is A with neighborhood is totalistic if F only depends on the number of cells in each state of its neighborhood in each state in its neighborhood, and not necessarily the exact position of those states. So formally we can say F is invariant under the full permutation group G being Sk. So essentially, no matter what states you plug in, and no matter what permutation you choose on these k neighbors, yeah, you get the same. So this reduces the space of rules to study dramatically, and it is a natural choice because this gives you some geometric symmetries. But maybe it's a bit too restrictive, so the other famous class are outer totalistic CAs. So F depends on the central cell. So we can assume that the first vector in the neighborhood is always 0. And the number of cells in each state. In the rest of the neighborhood. So formally, for each permutation from Sk such that the permutation preserves the 0th position, we have that so in this class we have exactly game of life and the larger than life rules, for instance. And the last, a bit of a more refined way we can reduce the space is not to restrict the local rule, but instead to only consider cellular automata with unique dynamics and discard all the ones that already have equivalent dynamics to R1 represented. This way we still know we will kind of cover all the possible behaviors we can see, but it can help us to reduce the space, though the reduction is not as dramatic as these two. So we can call this the CAs up to equivalence dynamics. And here the idea is to introduce some basic symmetries with which we can act on the set of local rules in some set. And then notice what is a good set of symmetries such that if we have two local rules that are, let's say, in the same orbit of this group action, they will actually have they will be isomorphic dynamical systems. So I'm gonna, let's say, illustrate this on the class of elementary cellular automata, but then the generalization is pretty straightforward. So for elementary CAs, there are two natural symmetries to consider. A is exchanging the role of the left and right neighbor. B is exchanging the role of the 0 and 1, the two states. So formally, let ECA be the class of all such local rules, of all local rules of elementary CAs, of all local rules. So here we can have, so in the case A, we have an action which simply takes some local rule and sends it to a local rule which has exchanged left and right. And then so-called also the dual CA is when we exchange the role of 0 and 1. So if we have a CA local rule, we send it to a CA where now we exchange the role of every input bit. So if this was a 0, this will be a 1, and so on. We apply this rule, and then we also have to exchange the role of the outcome, so we do 1 minus this. So this is a different local rule that we can call sigma of f. And now the crucial observation is that if we do this transformation, then the resulting local rule's dynamics is equivalent to the original one. So elementary CAs with local rule f and P of f are isomorphic. What is the isomorphism? We can call it the capital P from the space of all configurations to the space of all configurations, which will be a reflection along the axis going through the 0th state in some sense. So, so let's say the image of C at position I is just C at minus I. And similarly, elementary CAs with local rules f and sigma f are isomorphic. Can you guess what is the isomorphism here? We can call it a big sigma. So sigma C at position I it's going to become crystal clear once I show you the picture. But here, this bijection just exchanges the role of 0 and 1. So let me show you. Unfortunately, to show you, I have to roll this down. But maybe you can still see. So while this loads, we can maybe say let G be a group that acts on the set of elementary CA local rules that is generated by our two actions P and sigma. Wonderful. Okay, so in the line above, you see rule 110 and its rule table and a space-time diagram on a cyclic configuration of size 250. And here you see, let's say, a symmetrical rule which is obtained from rule 110 by exchanging the role of the left and right neighbor. So for instance, if this rule had from an input 1, 0, 0, the output 0, this rule will have that from 0, 0, 1, the same output. And this space-time diagram is generated by started from the reflected configuration, so using the bijection capital P. And you see that the space-time diagram you get is just a reflected space-time diagram of the original CA, so there's really nothing new going on in the dynamics of this rule as compared to this rule. And secondly, here you have the dual example where you just exchange the role of 0 and 1. So if you then start from a configuration where the role of 0 and 1 is exchanged, you obtain a space-time diagram where the role of 0, 1 is exchanged. Pretty straightforward, right? So the first observation, so we will make a series of observations about this group. So first of all, this group only has 4 elements, which is the identity, sigma, P, and sigma composed with P. Why is this? It's pretty easy to see that if you exchange the role of 0 and 1, and then you again exchange the role of 0 and 1, you get an identity. If you exchange the role of left and right neighbor, and then you exchange it again, you also get the identity. And it is also not hard to see that these two actions commute. That is, it doesn't matter if you first exchange neighbors and then states, because they're somehow two independent ways that you can act on the rules. And this is already enough to show this. So this is, let's say, our observation number 1. The observation number 2 is let X be in G and F be in elementary CA. Then then F and XF are isomorphic. Well, in this case, it's trivial because we only have 4 elements of this group, but even if we had more, every element in X is just a composition of some of these actions that we generated them with. So the corresponding witnessing bijection will just be a composition in the exact same order of the witnessing bijections. So that also should be clear. Yeah, we can say that F is equivalent to G if there exists some member of this group such that F is X of G. And it's clear that this equivalence is only between cellular automata with isomorphic dynamics. So we can only focus on ECA rules up to this equivalence. And from each equivalence class, we just pick one candidate, and we have ensured that we will not lose any dynamical behavior. So what you will see in the exercises is if we do this quotienting of this space by this equivalence, in this particular case we get 88 elementary cellular automata, and on the in the exercise class you will get to see that this is not. So okay, when you read some paper about elementary cellular automata, it almost always mentions this number, but it very rarely, and that I mean basically, and it just does not really explain where is it coming from. So at the exercises you will see this really niche, or like this very nice fun fact that you can actually, you get to compute this in an algebraically closed form using the Burnside's lemma. So this is our final application of it. And you will also see that you can extend this strategy to larger CA spaces and see how many unique CAs you get up to this equivalence. So are there any questions regarding this? So to summarize, we have, let's say in the previous lectures, we have focused on cellular automata that were very carefully handcrafted together with very carefully handcrafted initial configurations to show a specific behavior. And now we have completely changed the perspective, and we will keep this perspective for the next classes. And we are now asking, given a cellular automaton, what can we say about its behavior? What are the reasonable ways to parameterize the space of CA, and how typical is each of these behavior in that space? And this was our first, let's say, intuitive sneak peek into it. And now we will essentially spend at least 2 lectures talking about topological dynamical properties of cellular automata. And then we will switch into the computational properties of discrete systems. So maybe we can already start with the complete basic introduction to the topology in the CA space. Is this the right camera? I don't know. Surprisingly, yes. So for now, let us just again fix a CA, which lives in dimension D with state space S and global rule F. So the whole purpose will be now to enrich this space with subtopology, so we can talk about conversions, about continuous maps, and about other properties that cellular automata can have. So we introduce not even a topology, but a metric on the space, a metric D, not to confuse with the dimension, which is unfortunate, but this will be a sig D on the space as follows. So for 2 configurations, if we want to measure their distance, well, either this is 0 if they are equal. That's a good start for a metric. And otherwise, it will be a value 2 to the minus k, where k is the minimum of all the norms of vectors where these 2 configurations differ. C1 is different from C2. So again, next week, not next week, but next lecture, during the exercises, you will get to verify that this is indeed a metric. Indeed, D is a metric. So it's pretty straightforward, but to gain some more intuition into what's going on, we can look at the how do the open sets look like. Yeah, so every metric induces a topology, which induces a topology on to the Z to the D. So a basic open ball with radius 2 to the minus r centered in a configuration C is just BRC, which is the set of all configurations such that they agree with our center for all vectors whose norm is at most R. So the picture to have in mind, let's say in one dimension, if we have this radius R, so this is minus R, this is R. If we want to specify a ball centered at the configuration, we exactly care about the values of the configuration here, and then outside of this finite precision window, the configuration, or like, it can be anything. So, example of an open set. So, in 1D, we can consider the set U, let's say, of all binary configurations, such that C, I don't know, -1 is 1 and C2 is 0. And basically, this is an open set. Essentially, the reason is that if C belongs to U, and C prime agrees with C on the interval from -2 to 2, then clearly C prime also has the value at -1 equal to 1 and value at 2 equal to 2. So in particular, it belongs to U, which means the ball with radius 2 to the -2 centered at C belongs to U. So this is an example of this is a cylinder set, which is a set where we specify only finitely many values. Values of a configuration. And as you will see next lectures at the exercise classes, a few facts. Every cylinder set is open. The argument is always the same. The set of basic balls, of basic open balls, forms a basis for this topology. And so does the set of all cylinders. And so does the family of all cylinders. Yeah. And this is really not difficult to prove, but the metric space that we have just defined is compact. Okay, so maybe one last fact is for a fixed R, there are only finitely many balls with radius 2 to the minus r, which means the basis is countable. So this is really just some of the most standard properties of this topological space. I suppose after Easter we will return to the compactness. We will just briefly discuss what does it mean to be converging in this space, that you can kind of immediately see the compactness if you take the discrete topology on S and then take the product topology on S to the Z to the D, that will really exactly have the basis equal to the cylinder sets. And then from Tikhonov's theorem you have immediately that it is a compact space. So essentially we will see after Easter that this metric is like a nice natural metric when we want to study cellular automata, because we will have the following important characterization, that global maps of cellular automata are exactly such maps that are continuous with respect to this and commute with shifts. So it's quite easy to see that every CA's global rule is continuous with respect to this and commutes with shifts, but it also works the opposite way, and we have to use the compactness for that. So that's it. Yeah, hope you have a nice Easter. If you have any questions, you can come to me.